Okay, so we've started bivariate last term, and the first thing we did was significant numbers. So remember, the rules for significant numbers is you start counting as soon as you have your non-zero. So for this first number here, we saw 4 is a non-zero, so we'll start counting. And the first column, they wanted 3 significant figures. So I would have 1, 2, and when you get to the third one, you have to look like your normal rounding. And because that's a 3, I don't need to round the third one up. So then you'd write 4, 2. And when you have a number bigger than the decimal place, so bigger than 1, you still have to finish it off with zeros. So that it makes sense. So it's 4,210. If we wanted just one significant figure, we'd put the first one, we look at the second, it's only a 2, so I don't need to round that 4 up, and then I would write zeros after it. Now, just to look, decimal places are different, so let's go down to this one down here. If you look at that, if I was going to do 3 significant figures, I don't start counting until I get my first non-zero, which is the 9. So then I go 1, 2, 3, so I'll look at the third, but I've got to check the fourth to see if I round up. I don't need to. So this one would be 9, 2, 3. If I had to do one significant figure, I'd have the zeros, and then I'd just have that 9 there. Okay, so that was significant figures. Okay, we then are going to look at bivariate data where we have 2 numerical variables. So say, for example, I might have collected everyone's height and everyone's weight. Okay, so this is bivariate data, so say they were 167 centimetres and, 62 kilograms. All right, so we would have collected a whole heap, just making these up, blah, 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 blah. So bivariate data is when we're taking 2 pieces of information from the one source, and we in particular are going to be looking at it when it's 2 numerical data, and that's like what I've got here. Height and weight are both numerical data. So what we want to know is when we're drawing our scatter plots, if you remember, we have our scatter plots. So what we've got these axes, which have normally been our y-axes and our x-axes. So along the x-axis, we're going to have our explanatory variable. So our explanatory variable is the one that sometimes we might call it the independent one. So, and what we say, it's not, it's the controlled one. And over here on the other side, on the y-axis, we like to say we've got the RV, or the response variable. And that's generally, that's the one that we're looking at or measuring. So you might be saying, you're the one you're investigating or looking at. And we say it depends. It's the dependent. So it'll depend on the other one. So it's the dependent. So in this example of height and weight, you cannot change your height. Your height is going to be what it's going to be. But your weight may vary. And so what we say is that height is independent. So that would, down here, we'd have height as our explanatory and weight as our response. And so what we did that, and then I'm going to jump ahead a bit. So, and we ended up with scatter plots. And so we've got all these different individuals. So those dots would be all the people we looked at, and we've recorded their height and their weight. And then if you remember, what we did is we looked at those dots, and then what we said, we gave it a strength. And remember, if the dots were close to each other, close to following a straight line, we said it was stronger. So we measured the strength by using the R value. Now the R value was also known as Pearson's correlation coefficient. So sometimes they might call it that, sometimes they might call it just the R value. So if you had a look, if it was going upwards, it was going to be a positive R. If it was going down, it was going to be a negative. So if I was describing if I was describing this scatter plot that I've just drawn up here, I would say that this is a positive, and I'm going to say it looks pretty strong, positive, strong, and because the dots are following a rough straight line, we say linear relationship. So I'm saying that between height and weight in this data, I think that it has a strong positive linear relationship. So we looked in our calculator how to calculate the R value. So remember we were putting those lists in. So if I jump ahead here, we looked in. This one they were comparing, just in this little example here, they were comparing if test 1 and test 2. So we would have had test 1 here and test 2, and they were probably saying maybe they wanted to say the better you went on a test in test 1, the better you went in test 2 maybe. Anyway, so there's the thing. So if we were trying to find the R value, remember we put our 2 lists in. So here's my 2 EV and RV lists. And remember we went and found that R value on that list and spreadsheet page. So if you can't remember, ask me. And here's a description. Here's how you find the R value on the calc. So you got that in your notes. But here's how we measure that R. So if we get an R of, say for example, if I get an R value of 0.84, what type of relationship is that? 0.84. Good. That would be a strong, it's this one, isn't it? Strong, positive. Okay, what about if I got an R value of negative 0.3? Yep, it's coming from this one, so it's a weak negative. So really you just have to find the R value on your calculator and then you can describe your scatter plot. So we're going to skip over this, we'll do this Friday. I want to get up to this one. Alright, so today this is new, we're going to be looking at the coefficient of determination. So maybe up on your top of your page, I want you to put this is R squared value, okay? So they look similar, the names look similar. The R squared one has that determination. It's the coefficient of determination. The R one was correlation coefficient, okay? So be careful. So the R squared value, the coefficient of determination, it can simply be found by, you can simply just go R times R. So if you knew what the R value was, you go R times R and you'll get R squared, okay? But your calculator, when you go find, on your calculator, when you go find, you've got all your stats and you have your R value listed, say it was 0.8, your R squared value is also listed there. So you don't even have to calculate it anyway. It would be listed there. Okay, so what does the R squared value tell us? It tells us, so it's sort of telling us how much, say for the example of weight and height, it's saying how much of the change in everyone's weight, how much of that is due to their height changing, okay? So say for example, up here, so you can see they said the R value was 0.8. So when we found the R squared value, we said it's 0.64. So what we often do is change that to a percentage, so 64. So I'm going to say 64% of the change in everyone's weight is due to their height. So if you have a real tall individual, they're going to weigh more, aren't they, to a shorter individual. So 64% of that is what we're saying in our data. We're saying it's changing because of the height. Now, there's another 36% in there, and that would be other factors such as like, I don't know, someone doesn't exercise or, things like that. There is a lot of other factors. All we're saying is in this data that we're looking at, we see that when we change these the heights, we're seeing this change, that it's changing that much of the weights. So that's what we do. So you have to generally explain the R squared. They might say explain or interpret. So maybe over here, I'd like you to write, when it says interpreting, so you might write when you're asked to explain the R squared value. That's what you've got to do. You've got to write this statement. So I've written a statement that you just copy out, and in the yellow is the yellow parts mean you have to change. You change for the example. So the yellow parts you change for the example, for your example. So if you look at the one above, we talked about height and weight. So if I was going to explain the R squared value for this data, I would say, now you can see here, I'm writing out everything that's in black normally. So I write the coefficient of determination tells us that. Now here, this bit was in yellow, so I had to change it. And what it's telling you in brackets, what to do there. So you can see here in brackets, so you get your R squared value and you times it by 100. So we've done that. So the coefficient of that tells us that 64% of the variation. So you could use, they say variation, they might say change, it's the same thing. So the 64 of the variation in people's height. So you can see this was another thing we had to change because it says the response variable. So I've changed that because in this example it was weight, beg your pardon. So people's weight is explained by the variation in their height. So can you see the only bits that have been changed in that box is the things that were yellow, and that's what you'll need to do. So, and then underneath, it's just explaining if you got an R squared value of 30% or less, it's really whatever you're investigating isn't the major cause of what's happening. So we sort of say, well, therefore, we're not going to investigate this. It's not working. So say we compared, say we could get two numericals. Say we compared your, say the Year 12's height and their ATAR score. So you'll get an R squared value. It's too numerical. You can get an R value. It might end up being, 0.2 because it's got nothing to do with it really, has it? So you can get off things. And so we'll look a little bit about all of that stuff later. But mainly, you just need to write that out, okay? So it says calculating the correlation coefficient from the coefficient of determination. So here, this is a little bit different. They have given us the R squared. They've said it is 0.5210, and they want us to find the R value. So what I'm going to do is does anyone know what's the opposite if you square something? What's the opposite of squaring something? Yeah, good, square root. So what I'm going to do, R would equal either plus or minus the square root of 5210. So what you do is you just, in your calculator, you just find the square root of this number. So you type that into your calculator. All right, so we've done the square root of the number, that number, and we get this number, we get 7.7218, okay? Now, it's still, why I'm saying plus or minus is if you have -2 times -2, you get +4, don't you? And if I have 2 times 2, I get +4. Is that true? So if I said the square root of 4, you don't really know whether it was plus or minus, do you? You can't really tell. And that's why we always say, oh, well, it's either plus or minus 2. We don't know which one it is. But in this, because I've been given this diagram, so this scatter plot tells me that this is a negative relationship because it's going downwards, isn't it? So this scatter plot tells me it's a negative relationship. So if you have a negative relationship, therefore the R value would be what? Positive or negative? Would equal a negative. So I can actually now write the final answer. I can say R is actually negative 0.72180. And I only knew that because I can see the scatter plot. If I didn't, I'd have to leave both those answers there. I don't know which one it is. Okay? Okay, the data on the number of booze buses in the use and the number of drivers registering a blood alcohol reading over 0.05 was recorded, and the correlation coefficient was found to be 0.77. Calculate, so the first part of this question is calculate the coefficient of determination. So when I'm doing these ones, as soon as I read coefficient of determination, I just like to write above it R squared so that I don't stuff it up. Okay, so R squared we know is the same as R times R. So you can square the R. So we can say 0.7 squared. So we work out what that number is. So that's simply what they're asking us to do. So we'll just pop that in our calculator. So the R squared value is 0.5929. Now, it says if there was a causal relationship, state the most likely variable to be the... Oh no, don't worry about that. I'm going to change this question. I'm going to make my question B say interpret the R squared value. Okay, so I'm going to show you, we want to interpret the R squared. So in this example, so B, I'd be using that fill in the blanks, and I'm going to say the coefficient, so I'm using that table for the fill in the blank table box from the page before. The coefficient of determination tells us that, now I'm going to change that 59 to a percentage, so I'll change it to 59.29%, that's what you had to change, of the variation now you have to use the response variable, so I'm going to say the blood alcohol reading. I'm going to just say BAC, or what is it? No, B. I think it's BAC, isn't it? Yeah, blood alcohol content. So the variation blood alcohol content, or in the number of people with blood alcohol over 0.05. So that was, and the number of booze buses. So that, oh sorry, I've gone off track. So it tells us that the variation in the number of people over 0.05 can be explained by the variation in the number of, can be explained by the variation in the number of booze buses. This one is a little bit unclear with your EV and RV. Yours are a bit more clearer. But I've done it with you. All right, so these bits, this was your response variable, and this was your explanatory variable. Those were the things you had to change.